Welcome back. Sorry I had to cut that video short. My family just arrived home, so it was about to become chaotic. So in that last video I just introduced the idea. Let's just go through a bit of a more concrete example so that you understand what I mean by hypothesis testing. So I just watched the AFL Grand Final today, and we had a player called Tom Boyd playing for the Western Bulldogs who won. And Tom Boyd has been an okay player, but today, in the last couple of weeks, he's been really good. And what we might want to ask is, well, we've got this player who's been, kicking a certain number of goals every week in the footy, but in the last couple of weeks, he's kicked more. He's kicked more goals. And so what we want to know is, has Tom Boyd improved? We want to know, okay? And so what we're really saying is that that's our null, well, it's not a null hypothesis, that's the hypothesis that we want to check. And so let's just set this up. So let's just actually stick some numbers on it. So let's say that Tom Boyd averages 1.2 goals per game. Okay, that's over his career, over the last few years, 1.2 goals per game. With a standard deviation of 0.5. So it might be more than that, might be less than that, but the standard deviation is 0.5. Now let's take a sample of 4 games. So the last 4 games that he's played, his average is 1.9. So let's have a look at this. His career average is 1.2 goals per game. In the last 4 games, he's averaged 1.9. So what we want to know is, has Tom Boyd improved? So looking at this, I'll just change to a nicer colour. Our null hypothesis, remember, the null hypothesis says that nothing has changed. In other words, Tom Boyd has not improved. The way we say that mathematically is that then the average is still equal to 1.2. Nothing has changed. His average goal kicking is still 1.2, but these last 4 games have just been an aberration. He just happened to have kicked more goals in the last 4 games, but pretty soon that's going to go back down to being 1.2 or less, so averages out as 1.2. So nothing has changed. The alternative hypothesis is that Tom Boyd has improved. The way we'd write this mathematically is that mu has got bigger than 1.2. It's increased. We don't know how much by, but we're just saying that it has increased, and that this this value here is actually representative of the fact that he has improved. And so that's what we're looking at here. And how do we actually decide this? What we have is called a z-test, and we're going to look at what this is, and this just helps us calculate the probabilities, okay? So I'll come back to the z-test. What the z-test does is it looks at a p-value, and what this stands for is the probability value. So the p-value is the probability that, assuming h0 is true, okay, so assuming that nothing has changed, assuming that h0 is 10, that you would get a value for x bar equal or more extreme. Than the x bar that you're looking at here. So, in other words, our p-value for this particular example is the probability that, assuming that the mean is 1.2, what's the probability that you would get a value of 1.9 or greater? Okay, so what we're looking at here is that if we've got our standard distribution like that, then if 1.2 is in the middle, and we're getting this value out here of 1.9, what's the probability of getting this value or greater than that? What's the probability that that's happening? And that's asking the question, given if H0 is true, what's the probability of getting something like this? If it's astronomically small probability, then that means that we don't really think that that average could be 1.2. It must have increased. But if it's quite high probability, there's a good chance that you get a sample mean of 1.9, then it probably means no, the H0 is true and that the mu is still the same. And so that's what we're looking at here. So the p-value, the probability that assuming H0 is true, so assuming mu of 1.2, that you get a value for x bar equal or more extreme than 1. So in other words, P is equal to the probability that some x bar is greater or equal to 1.9 given that mu is equal to 1.2. Okay? Probability that given that mu is equal to 1.2, what's the probability that you get a sample mean greater than 1.9, greater or equal to? And that gives you the p-value. So that tells you the probability that that H0 is true. From that p-value, you can then make the judgment of whether H0 is more likely or H alternative, H1 is more likely. So we'll look at that. That's your p-value, and it comes under a z-test. That's what it's called on your calculator and that sort of thing. The p-value is just your probability. So let's have a look at that. For this Tom Boyd question here, let's have a look at what the p-value is. So we've got the probability there. I'm just going to go to a new screen. So looking at that value, I'll just write them all down again. We had mu was equal to, I have it on my sheet somewhere, 1.2. We had a standard deviation of 0.5. We had a sample size. Oh, I didn't write this down, sorry. We're going to take his last 4 games. So we're taking a sample of his last 4 games and we're going to have a look at what happens. And for those last 4 games, we got an average of 1.9. And so what we want to look at is the p-value. So the p-value is the probability that x bar is greater or equal to 1.9. So equal to this value or more extreme. What's the probability of that happening? Let's have a look at it. Okay, and so that's equal to the probability of z, let's go to our z statistic, that's why it's called a z-test, of 1.9, that's the value we got, minus the expected value, expected value of x bar over the standard deviation of x bar. Okay, so that's just because we've got x bar here. We've done that all before. So that's the probability that z is greater or equal to 1.9. What's the expected value of x bar? The expected value of x bar is equal to the expected value of the population, so that's minus 1.2. Over the standard deviation, what's the standard deviation of x bar? Well, that's, I'll just write it up here to remind you. Standard deviation of x bar is sigma over root n. You remember that from past videos. So that's equal to sigma is 0.5 and root n is root 4. So that's what we've got there. So that's actually pretty simple calculation. That's the probability that z is greater or equal to 1.9, that's 0.7 divided by 0.5 is effectively doubling, so that's 1.4. So that's 1.4 times by 2, so that's 2.8. Okay, probability that z is greater or equal to 2.8. You then get your trusty calculator out because you're lost without it. Menu, probability, distributions, normal CDF. We wanted to have 2.8 up to infinity. So that's the probability of it greater than 2.8, and that's 0.002555. 0.025, we'll just go 256, okay, which is approximately equal to that, approximately equal to, let's just put it in percentages so you can sort of see the weight of it. That's 0.256% chance. So what we're saying, Tom Boyd has an average of 1.2, standard deviation of 0.5. We've taken the last 4 games as a sample size and we've got an average of 1.9. The probability, if the population mean has not changed, the probability that we'll get something like this, or more extreme, is 0.256% chance. This is really low. what that means is that the probability that the sample mean has not changed is really low. In other words, H0 is really unlikely. It's really unlikely that nothing has changed because this percentage is so low. Hope that makes sense, because this is the guts of what we're doing in this topic. And this question, and the next question that you're probably going to ask is, well, how low is too low? So I'm just going to move on a slight bit now, because we're going to look at this. So 0.256%, that's what we've got here. What we need to know is how low is too low, and that'll always be stated in the question. And what we want to know is the level of significance. Okay, and we call that value alpha. And in the question, the alpha will say it might be 5%, these are the usual ones, 1% or 0.1%. And what the question will say is, decide whether Tom Boyd has actually improved the number of goals per game he's scoring to a level of significance alpha equals 5% or something like that. And what that means is that if the probability is less than one of these values, then you can say you can reject H0. Okay, so I'll just write that down. So I'm just going to remember that number, 0.256%. So for the Tom Boyd, we've got 0.256%. That's our probability. And so what we're looking at, so if P is less than 5%, then we reject H0. H0 is unlikely to be true because that probability is so low. So there we're looking at 5%, and we get for different values depending on what's going on. So we're looking at each different alpha size. So a question might say, the Tom Boyd question, find out whether Tom Boyd has improved. Improved to a significance level of 5%. Okay, so it might say something like that. And so you look at the p-value. If the p-value is less than 5%, then you reject H0 in favour of the alternative hypothesis. In other words, this percentage is so low that the null hypothesis cannot be true, or is very, very unlikely to be true, and therefore we think that Tom Boyd has improved. So that's what we're looking at. So let's say this question said, oh, let's just do that again, sorry, of 5%. You look at the value. Is it less than 5%? Yes. Therefore, since P is less than 5%, we reject H0 in favour of the alternative hypothesis. Let's change this. Let's say if it is, let's change this to 1%. What if the question asks whether it's Tom Boyd has improved to a significance level of 1%? We need this p-value to be less than 1%. Is it less than 1%? Yeah. That p-value is less than 1%, so we still reject it. What if we go to a level of 0.1%? Is p less than 0.1%? No. P is greater than 1% in this case, and so we accept H0. Okay, so what we're looking at, we're comparing the p-value to our significance level alpha, and if p is less than alpha, then we reject. I'll write this on a new screen. I'll make it really, really clear. So we're given, always you get given significance level alpha. If your probability is less than alpha, then reject your null hypothesis. It's just very, very unlikely that it's true. If p is greater than alpha, then we accept H0. And that's what we're doing here. And basically, that is hypothesis testing. Until you do a few of these and try to wrap your head around it, it might be a little unclear, but that's what we're looking at here. Remember, null hypothesis means nothing has changed. Alternative hypothesis means something has changed. Something has increased or something has decreased. And that's hypothesis testing. I'll see you in the next video.